Hi folks, somebody asked if I could make a answer key for your sample, so I thought if I'm going to do that I might as well film doing it so you can hear me blab about it. Hopefully that's helpful. I am going to though have to do it very quickly, just try to make the time a little bit smaller, so some of them I might allude to, but we'll see how it goes. So determine the local extrema. Local extrema are our max and our mins. You're told the scale is 1 to 1, so that point is happening at 1, 2, 3 in the x, 1, 2, 3, 4, 5 in the y. So the first local extrema we have is the point 3, 5. The local minimum down here looks like it's at 1, 2, 3, 4, 5 negative in the x. And 1, 2, 3, 4, 5, 6, negative 6 in the y. You generally will want to say that things are what they are. This is a relative max, and this is a relative min. To find the equation is a little bit more complicated. To find the equation, we want to find its roots. Its roots are going to be its x-intercepts. So its x-intercepts are negative 1. So I'm going to make a little note of that. X equals negative 1 is an x-intercept. 1, 2, 3, 4, 5, 6, 7, 8. X equals 8 is an x-intercept. And 1, 2, 3, 4, 5, 6. Looks like x equals 6 is an x-intercept. It also looks like it has a y-intercept there at 2. So it has a y-intercept at 0, 2. Now, one thing to keep in mind about this sample, you certainly, I put this problem here because it was small, but you don't want to be, doing your answers and squeezing your stuff into this test. Do it nicely on some other piece of paper somewhere. Try to get your focus to work. There we go. Actually, I want to turn that off. Okay. So if we have these x-intercepts, it's nice to remember that if you have an x-intercept, or often called a root or a zero of a polynomial, for example, if that 8 is an x-intercept, a root, and a 0, that means the factor x minus 8 must be one of your factors. X equals 6 as a 0 means x minus 6 is a factor. X equal negative 1 being a root, an x-intercept, a 0, means that x minus negative 1 or plus 1 must be one of your factors. We also have to keep in mind that there might be some constant a, some lead coefficient that's going to make this move exactly the way it's supposed to move, and that's why I wanted to grab this y-intercept. So we have to make sure not only that it has these proper zeros in it, but that it also goes through this particular point. Because there are a lot of polynomials that have those zeros. That's another one. You could make one here. That's got those same zeros. We want the one that goes through this particular point, and that a is going to control it and make sure that f of 0 is going to equal 2. So we could certainly multiply this together. So we're supposed to build a polynomial, so we probably should. Our polynomial is going to be of the form a times, multiply this together, what do we get here, x squared minus 7x minus 8 times x minus 6. Multiply the x minus 6, and we get what, x to the third minus 6x squared minus 7x squared minus 8x plus 42x plus 48, I think. Again, I'm trying to do that really fast. So if I did something overly bizarre, please excuse me. But this would end up being, what, 34 plus 34x plus 48. So this polynomial has the right x-intercepts in it, but to make sure that f of 0 equals 2, we have to make sure that if we plug in a 0 here, we get 2. So this thing is supposed to equal 2 when a times, let all those be zeros, 0 minus 0 minus 0 plus 48. This has to equal 2 when we have the right value for a. So 2 is supposed to equal a times 48. Divide the 48 off. 1/24 should be a. So that makes our overall polynomial p of x equal to 1/24 times the x to the third minus 13x squared plus 34x plus 48. And you could certainly multiply that 1/24 through, but frankly, when it's a kind of an icky fraction like that, I tend to leave it outside. But that's really up to you. So the key for building these polynomials is you will either be told your roots, as you often were in the homework, or from a graph, we should be able to observe our roots, and then we should be given some other piece of information, some other known point, to make sure we have the right coefficient. Notice that a, if you distributed this in, that a would become the lead coefficient. Just making sure we have the right lead coefficient to make it go through the proper point. So that's number 2. And that a is usually what people leave off. Number 3 is actually a very, very similar problem. This is the other kind of look for that problem. Given that you have roots at x equals 2, 3, and -1, you want to be a degree 3 polynomial. It's got 3 roots, so that makes sense, such that f of 1 is equal to 2. So it's really a very, very similar problem, except instead of being given the information graphically, we're given the information just in the values. But again, if 2 is a root, then x minus 2 must be a factor. If 3 is a root, x minus 3 is a factor. If -1 is a root, x plus 1 must be a factor. And we might have some constant a that forces this to happen. Now, last time I multiplied all this together. You can actually find your a value before doing that if you want to. This again is supposed to equal 2. They both happened to equal 2, just because. But this is supposed to equal 2 when x is equal to 1. So you can actually put those 1s in early if you want to. 2 equals a times, what, -1, -2, and 2. So 2 is equal to a times, what is that, -4, so 4. Divide the 4 off, and a is equal to 1/2. Sorry. So we now know that our polynomial should look like 1/2 times x minus 2, x minus 3, x plus 1. And because we were asked for the polynomial, you probably want to write that out. You perform your multiplication, so it's in your fairly standard polynomial form. But I'm assuming you can do that. The key to this problem is the same as the last one, to recognize that these x-intercepts, or these roots, or these zeros, represent those factors, and then making sure we have the lead coefficient, the a, that's going to make the given point work. Let's see, 4. You were asked to find the exact zeros. I should probably number these. 4. That was 3. Okay, so remember those. So find the zeros, and you were asked exact zeros. That means don't use your calculator, essentially, of f of x equals x to the third minus 33x plus 18. Now, if this was a quadratic, you would just set equal to 0 and factor. But it's not a quadratic, so we can't factor it. You might use the quadratic formula, but again, for the quadratic formula, it has to be a quadratic. So to find the zeros, to find the x-intercepts, to solve, to factor a larger degree polynomial, like this x to the third minus 33x plus 18, which again we are going to want to set to 0 because we are trying to find its zeros. We want to use those tools in the middle of chapter 4, in 4.3 and 4.2. Sorry, yeah, 4.2, 4.3, and 4.4, where we tried to figure out what roots this has to try to determine what possible things we should try dividing out of it. And those sections talk about a couple different ways to do that. One was your rational root theorem to find your possible rational zeros. So the factors of 18 over the factors of the lead coefficient. So the factors of the constant are what? 1, 2, 3, 6, 9, and 18. And then, of course, positive or negative. Nice thing in this one, Q, the factors of the lead coefficient are just positive and negative 1. So our possible rational zeros are just 1, 2, 3, 6, 9, and 18. Now that is what, 6, and then with the positive and negative, 12 possible values that might be zeros, and that would take a while to check all of them. But the nice thing is we don't have to check all of them. We just have to find one or two that work. And there's a couple nice things to do to try to hone in on ones that might work. The big couple are Descartes' rule of sign that's in your texts. It's kind of an old-fashioned tool. It's a nice one to look at, but it's not something we'll use terribly often. The other one is to go to your calculator and graph this thing. If you graph it, you will see some x-intercepts. I don't know exactly what this graph looks like, but it's going to have a couple x-intercepts. It might only have one x-intercept. But that'll give you a sense of which one of these you should try. But we really could just start picking them and throwing them in, seeing which one works. For example, if I want to try, I'm going to try 2. We can test to see, is 2 a 0? To check and see if 2 is a 0, we can do our synthetic division. Do the synthetic division with 2. We have to list our coefficients. The coefficient of the x to the third is a 1. We notice that there's an x squared missing, so we do have to put in the 0x squared. Not doing that is very dangerous. And then negative 33x plus 18. So we can probably see a little bit that this isn't going to happen really nicely. Bring down the 1, 2, add them together, 2, 4, 4 and 33 is going to make a 29? Negative 29? Yeah. And then 2 times negative 29 is going to be negative, 58? And that's so not giving us the 0 that we want. So clearly that's not working. We need something bigger. So maybe try the 3 or the 6. Let's try the 6. And you just try stuff until you find something that works. The graph isn't really nice though. Look at the graph. If we looked at the graph and it didn't cross anywhere near 2, we wouldn't try 2. But let's try the 6. So 1, 6, 6, 36, 3. Oh, that almost wants to work. 6 and 3 is 18. And that's what, 36 again. So that didn't work, but it seemed to be trying to. What if it was a negative 6? If it was a negative 6, that would have been negative 6, negative 6. That would have been positive 36. Still would have been a 3, but that would have been a negative 18 and a 0. So sometimes if we just play with it, we can kind of get a sense of what numbers might work nicely. But again, use the graph. The graph helps a lot. Your textbook talks about that. So what we have found here is that x plus 6 is one of our factors, because that's one of our zeros, and that's a 0 that worked. Now we don't have to keep checking, because we now know that if we divide out the x plus 6, the rest of the polynomial is x squared minus 6x plus 3. And this is something that we can set equal to 0 and solve separately, because it's a nice quadratic. Now that quadratic, it doesn't look like it's nicely factorable. It certainly is not nicely factorable. So it might take a little bit of quadratic formula. So negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 3 all over 2. And clean this up to get your other two answers. Other two answers. And again, I'm going to assume that you guys can do that. So you're going to have negative 6 as one of your solutions. And your other two solutions are going to come from the quadratic formula. And they will be things like, oh, that looks like it may be, yeah, let's just do it. That's what, 12, so it's 6 plus or minus the square root of 24 over 2. The 24 is 4 times 6, so 6 plus or minus 2 root 6 over 2. So how about 3 plus or minus the square root of 6? So your answers are negative 6 and 3 plus or minus the square root of 6. You guys can do that work. But that's what I mean when I say exact zeros. This is an exact value. I don't want the decimal approximation. I want the exact but reduced value. So the big thing is kind of coming up with this list of possibles using your rational root theorem, or using the graph to get a sense of what's possible. Or actually, I like a combination of both. So play with those. But you want to make sure that this idea with the synthetic division that we get at the middle of chapter 4 is coming up whenever you're trying to break down large polynomials. Okay, so that's 1, 2, 3, and 4. I'm going to split this into a couple different videos, so I'm going to stop there and start it again on number 5.